Hi, students. Welcome to today's session. We are doing magnetic effects of electric current. That is our chapter 13. Okay. First of all, let us see what are the objectives in this chapter. We have to learn magnetic field and magnetic field lines. To plot the magnetic field pattern due to a bar magnet, then properties of the magnetic field lines, magnetic field of Earth, magnetic effect of current, experiment to demonstrate the magnetic effect of current, magnetic field pattern due to a straight current carrying conductor, direction of magnetic field produced by a straight current carrying conductor, right hand thumb rule and Maxwell's corkscrew rule, magnetic field pattern due to a circular loop or circular wire carrying current. Then magnetic field due to a current carrying solenoid. You will learn what is solenoid. Then electromagnet, magnetism in human beings, force on current carrying conductor placed in a magnetic field, Fleming's left hand rule for the direction of force, electric motor, electromagnetic induction, electricity from magnetism, Fleming's right hand rule for the direction of induced current, direct current and alternating current, then electric generator, domestic electric current, earthing of electrical appliances, short circuiting and overloading, electric fuse and miniature circuit breakers, that is MCB, hazards of electricity. Okay. So then precautions in the use of electricity. These are the main points what we are going to learn in this chapter. Fine. So magnetic effect of electric current. Before we have learned heating effect of electric current. If the current is passing through some circuit, some resistors, some devices, it is producing heat. That is heating effect of electric current. And when the electricity is flowing, if it is giving light, then we can say it is a lighting effect of electric current, right? Similarly, if the current is passing, electric current is flowing through a conductor, and we are getting magnetic properties, that is magnetic effect of electric current. Due to the flow of current, if the magnetism is appearing, then we can say magnetic effect of electric current. Okay. So the term magnetic effect of electric current means that an electric current flowing in a wire produces a magnetic field around it. In other words, electric current can produce magnetism. Okay. See, we will take an activity. Take about 1 meter long insulated copper wire and wind it round and round closely on a large iron nail. See here, the picture I have seen here. We have a iron nail, right? It is wounded by insulated copper wire. Okay. Now, then connect the ends of the wire to a battery. So you can see it is connected. The end of the wire is connected to the battery. See, this is connected here, and this part is connected here. You see, right? Positive and negative. Now, we will find that the large iron nail can now attract tiny iron nails towards it. This has happened because of an electric current flowing in the wire has produced a magnetic field which has turned the large iron nail into a magnet. So the large iron nail is a temporary magnet due to the flow of electric current. Understood? Okay. So you can see that small iron nails has been attracted due to the magnetism. Magnet can attract iron, cobalt, nickel, etc. Fine, you can see that here. Now I will show you the activity. See, there's an animation for that activity. Switch on, switch off. When we are switching on, the big iron nail becoming a magnet, electromagnet, and it is attracting the paper clips. When it's switching off, the magnetism disappear and the pins get down. Okay, so this is a magnetic effect of electric current. On the flow of electric current, we have magnetism. Okay, fine. Now, see, and note that current carrying straight electric wires, like an electric iron connecting cable, do not attract the nearby iron objects towards them because the strength of magnetic field produced by them is quite weak. So don't think that whenever there is a current is passing, there will be an magnetism will be there, magnetic field will be there. Due to that, the nearby magnetic materials, iron, cobalt, nickel, etc., steel can be attracted, right? Don't think like that. So it will be difficult, right? So actually, if the electric field is strong, then only this attraction will take place. Okay, like in the case of iron, what I have shown you, right? See this iron. This iron nail is wounded by, see, the insulated copper wire and connected to the battery. And when we are switching on, so this iron nail becoming a powerful magnet. That is why it is attracting small paper clips or iron nails. Okay, fine. See, this is our electrical cabling in our countries, what we can see, right? So there are magnetic fields are there around current carrying conductors, right? But it is not that much powerful. Otherwise, if a car is going, it can attract to the top, right? The car and arm will hand it here, right? The car will be here. So it won't happen. Understood? Fine. Now, different models of magnet. A magnet is an object which attracts pieces of iron, steel, nickel, and cobalt, etc. Simply, we can say definition. Everyone know that simple definition. Magnets come in various shapes and sizes depending on their intended uses. See, we have a bar magnet. See, this is a bar magnet. There will be a north pole and there will be a south pole. This is a ring magnet. This is horseshoe magnet, normally using in laboratory purposes. Okay, labs we are using that. Magnetic needle. This you can see in compass. You know what is compass? right, to see the direction. Then we have disk magnet. Fine. Okay. Next, one of the most common magnet is the bar magnet. What is the common available model? Okay. A bar magnet is a long rectangular bar of uniform cross section. So it is. See, already I given you the figure, but even though uniform cross section, right? Uniform cross section. Everywhere this cross section will be uniform. The cross section will be uniform. That type of magnet is bar magnet. Fine. Okay. Now, poles of magnet. What do you mean by poles of magnet? A magnet has two poles near its ends. One is north pole, other one is south pole. Okay. Only two poles. Not like east, west. No. North pole and south pole. Only two poles. The end of a freely suspended magnet or a freely pivoted magnet which points towards the north direction is called the north pole of the magnet. Suppose if you have a magnet, see, I have a magnet here. Okay, this is a magnet, and I have pivoted this one. Okay, or I have just suspended. Okay. Now this magnet can freely move, it can rotate. After that, if this end is coming to the north, then the end will be the north pole. So opposite pole will be the south pole. So always a magnet, its north pole, it will come towards the north pole, and south will come towards the south. Understood? Fine. So we can say the end of a freely suspended magnet or a freely pivoted magnet which points towards the south direction is called the south pole of the magnet, which is directed to north pole. The north is north pole. Okay. Poles of magnet. Again, you can see some picture. This is our bar magnet. This is horseshoe. Horseshoe magnet. Okay. Horseshoe magnet. So this bar magnet, here we have north pole, here we have south pole. Similarly, the horseshoe also, there is north pole and south pole. Don't think that here north and here south. No, it is not here. In the case of horseshoe, it will be like this one. Okay. So the pole of a magnet that points to the north is called the magnet's north pole. The opposite end of the magnet points to the south. It is called the magnet's south pole. Magnetic poles are always in pairs. You will never find a magnet that has only a north pole or only a south pole. Okay. Even if you break this one, suppose if you break this one, change it into two pieces, right? So first piece, this side will be north and this end will come automatically south. And other part, this was already south. So this part will come automatically. So there is no magnet with one pole. Okay, always should be pair. North and south should be there. Okay, now basic law of magnetism. What is basic law? The basic law of magnetism states that like magnetic poles repel each other, while unlike magnetic poles attract each other. So like poles, same poles, repel. Unlike pole, dislike, right? Not same. They will attract each other. See the figure I have given you. This is a magnet. We have south and north. So this here south and north. So this south and north. See here north, here south. So they are unlike. What happened? They will attract. This will come this way. This will come to this way. Attract each other. Second case. Here the second. This is the first case. This is second case. Here south and here north. Here north and south. So north and north are coming face to face. So we can say unlike poles. What happened? They will repel, reject. It will go like this. See here south and south, right? Same pole, like poles. What happened? They will repel. So that is the basic law of magnetism. The basic law of magnetism states that like magnetic poles repel each other while unlike magnetic poles attract each other. Okay, now I'll show you the animation. Okay, some more point what I have written is this means that north pole of a magnet repels the north pole of another magnet, and the south pole of a magnet repels the south pole of another magnet. But the north pole of a magnet attracts the south pole of another magnet. This is the animation. See. Okay. North and south attracting. North and south attracting. North, south and north. South and north. Here see. North and north repel. North and north. Again south and south repel. Understood? So opposite poles attract each other, right? And same poles repel. Fine. Next, uses of magnet. Magnets are used in radio, television, and stereo speakers, in refrigerator doors, on audio and video cassette tapes, on hard disks and floppies, for computers, and in children toys. Magnets are also used in making electric generators and electric motors. The magnetic resonance imaging, MRI scanning, all these things, right? Technique which is used to scan inner human body parts in hospitals also uses magnets for its work. So there are wide usages there for magnet. Everywhere we can see the magnet, very useful property, correct? Fine. See some animation I have given you. This is the MRI scanning picture. Here you can see a battery is connected, right? So a coil is rotating. A coil is placed in a magnetic field, U-shaped magnet, right? So when we are passing electric current, what happens? That coil will become a magnet. That magnet is placed inside another magnet. So these two magnets will interact each other, and there will be a force of action will be there. Due to that reason, you can see that coil can rotate. So this is a miniature what I given for the model of a motor, okay, small motor that we'll learn in later, I mean the coming sessions. We have to learn in details. Okay. Now, what is compass? Compass. Everyone know that. What is compass? Right. Daily life. Lot of usages are there to see the direction. Okay. Ancient day, it has very importance because mainly in ships, they want to find the direction. They were using the compass. So, what is the definition of compass? A compass, it is a small magnet. See what is rotating inside? That is actually a magnetic needle. Its one end, which points towards north, is called north seeking or a north pole. North seeking pole or north pole. And the other end, which points towards the south, is called south seeking pole or south pole. So this part, the red is always seeking north. Right? This is seeking. So this part will become north pole. This we can call it as north. This is north pole. This part is south seeking. So that is south pole, south seeking pole or south pole of the needle of the compass. Or we can say it is the south pole of the compass or north pole of the compass. Fine. Okay. Now, magnetic field. Magnetic field, very important term in magnetism. What is magnetic field? Just as an electric charge creates an electric field, in the same way, a magnet creates a magnetic field around it. Suppose if we have a charge, we have a charge, positive charge, something. Okay. So there will be electric field will be there around this. Okay. Electric field will be there around this charge. Fine. Similarly, magnet creates magnetic field around it. So this red color is a bar magnet. This is the south pole and this is the north pole. Around this, see in blue color, you can see the magnetic field lines. Okay, so the region around this magnet where the interaction of magnet is taking place, attraction or repulsion, that region is known as magnetic field. Okay. So the space surrounding a magnet in which magnetic force exerted is called a magnetic field. The space surrounding a magnet in which magnetic force is exerted is called a magnetic field. That's the definition you have to remember. A compass needle placed near a magnet gets deflected due to the magnetic force exerted by the magnet, and the iron filing also cling to the magnet due to the magnetic force. So magnetic interaction, attraction or repulsion will take place in some region. That region is known as magnetic field. So we suppose in this much range, suppose if you are getting magnetic field, attraction or repulsion. So we can say at this range we have magnetic field. But theoretically, magnetic field going to infinitely. Infinitely it is going to the space everywhere, we can say. That's the theoretical part. But practically, we will have some region where we can say we have magnetic field. Okay. Now, magnetic field is a vector quantity. Magnetic field is a vector quantity. What is vector quantity? We have learned that There are two types of quantities. One is scalar quantity, scalar quantity. Another one is vector quantity, vector quantity. What is the difference between this one? Scalar quantity, it has only magnitude, only magnitude. It means when you are saying that quantity, you have to just say its numerical value, like it is like 5 meter, 10 kilogram. Now the time we can say 10 o'clock. Similarly, just we are saying the magnitude only, they are coming under scalar quantity. What is vector quantity? It has both magnitude, that's both magnitude and also the direction, and also direction. Fine. So just the magnitude is not enough. You have to say the direction also. Such physical quantities are known as vector quantity. Okay. For example, suppose I have a more, let it be a bar magnet. Let it be a magnet. I'm just saying, I applied a force of 50 Newton on this bar magnet. In which direction it will move? Which direction it will move? Some people will say it will be in the north direction. Some will say it will be south direction, or south, west, east, etc. Right? Fine. But all such answers will not be correct unless otherwise I have to say that I have applying 50 Newton force in which direction, right? So just this is a force just saying with the magnitude only will not give the complete sense. You have to say the direction also. So I'm saying if I'm applying 50 Newton in the direction of north, then we can say that this object will move in the north direction. If I'm applying a force in the west, it will move in the west direction. Okay. So such physical quantities are coming in vector quantity. Clear? Magnitude is not enough. Its direction also has to be specified when we are discussing. Such quantity is coming under vector quantity. So magnetic field is also a vector quantity. Okay. The magnetic field has both magnitude as well as direction. The direction of magnetic field at a point is the direction of the resultant force acting on a hypothetical north pole placed at that point. So we have a bar magnet. Around that we have a magnetic field. In that magnetic field, we are keeping a small compass. Small compass. Okay. So in the small compass, there is a needle will be there. Correct. So that needle will align in definite direction due to the interaction with the bar magnet. So that bar magnet magnetic field, its direction can be found using this small needle inside the compass. Okay. So by definition, we can say the magnetic field has both magnitude as well as direction. The direction of magnetic field at a point is the direction of the resultant force acting on a hypothetical north pole place at that point. Imaginary north pole. We are just keeping an imaginary north pole. Okay. Fine. So which direction it is getting the force? That direction will be the direction of the magnetic field. Okay. See, the north end of the needle of a compass indicates the direction of a magnetic field at a point where it is placed. See, we have a magnet here. We have a magnet. This part is a mark. This is our magnet. This magnet has a north pole. This is north pole, and here we have south. Okay. So around this bar magnet, in the space around the region around this bar magnet, where the influence of magnet will take place, interaction of magnet will take place, that is attraction or repulsion. That region is known as magnetic field. Understood? So magnetic field has both magnitude as well as direction. The direction of magnetic field at a point is the direction of the resultant force acting on a hypothetical north pole placed at that point. Fine. It's clear at this point. Okay. Now magnetic field lines. Magnetic field and magnetic field lines, both are two terms. What is the magnetic field? Space around the magnet where the properties of magnet, attraction or repulsion is taking place. Correct? Let us see what is magnetic field lines. Magnetic field lines. Magnetic field lines or magnetic lines of force. Another name is magnetic lines of force are the paths along which an imaginary free north pole would tend to move. See, in the animation I have seen an imaginary north pole. That red color is north pole. See that when you are placing in this magnetic field, it cannot move any direction. It can move only through some specific lines, curved lines. See, this north pole is moving, see, only through this line. So this line is a magnetic field or magnetic field line or magnetic lines of force. So magnetic force is acting through these lines. That is why we are calling it as magnetic lines of force. Understood? So if you are keeping this here it will move like this. If you are keeping here, it will move like this. If you are keeping here, that north pole, free north pole, if you are keeping here, it will move like this. Correct? Got it? So magnetic field lines or magnetic lines of force are the paths along which an imaginary free north pole will tend to move. Now, the magnetic field lines are the lines drawn in a magnetic field along which a north magnetic pole would move. That's the definition. First one is better. Some books will say like this also. So the magnetic field lines are the lines drawn in a magnetic field along which a north magnetic pole would move. So drawing isn't just for an interaction with us, right? But actually, even if you are not drawing, the magnetic field line is there. Invisible magnetic field lines are there, right? Drawing just to understand and doing some kind of experiment. That's all. Now, more on magnetic field lines. The direction of magnetic field line is the direction of the force on a north pole. Suppose if you have north pole, that north pole we are placing in the magnetic field, in which direction it is experiencing a force, that direction will be the direction of magnetic field. See previous slide, I have shown you this one, right? See why this free north pole is moving through a specific line, because it is experiencing force through that line only. It is experiencing a push or pull. It is taking place through this point only, this through point only. Correct? Understood. So that is the definition what we are saying. Okay. The magnetic field lines always begin from the north pole of a magnet and end on the south pole of the magnet outside the magnet. Outside the magnet, the direction of magnetic field start from north and end at south. Common convention. So understood that magnetic field lines always begin from the north pole, never from south. Okay, and end at south pole, outside the magnet. Take it care, outside the magnet. So it means inside it will be different. Inside it will be different. So in inside, it is starting from south to north. See, from south it will come to the north. Outside it is, see, north to south direction. But inside it is from south to north. So all over it is a closed curve. Closed curve. Inside the magnet, the direction of magnetic field lines is from south pole of the magnet to the north pole of the magnet. Now, the magnetic field lines are closed curves. So you can see that if you take this line, it is outside is starting from north. Outside starts starting, yeah, north to south, north to south. Inside what's happening? It is from south to north. So completely it is a closed curve, a specific closed curve. Okay. See, in this animation, you can see force is experiencing in the direction of north to south. All these arrows are traveling from north to south. So just think that that arrow is a freely moving north pole. It's an imagination only, hypothetical. Never there will be a single north pole will not be there, right? But as a definition, we would say like that. Fine. Magnetic field lines. When a small compass is moved along a magnetic field line, the compass needle always sets itself along the line tangential to it. What is tangential? See, if you have a circle. Tangent means what? A line which touches the circle at one and only one point. I suppose if you want to draw a tangent here, then what you have to do? See, this is the tangent at this point. At this point, we can draw a tangent like this. This point we can this tangent. This is the tangent. The tangent means a line touches the curve or circle at only one point. Such lines are known as tangent. So this is a tangent to the curve. So when a small compass is moved along a magnetic field line, the compass needle always set itself along the line tangential to it. So here we have a bar magnet. See, this is our bar magnet, and we are using a small compass. This circle indicates a compass. One side is north, other side is south. If you keep it here, see, if you are keeping here, what happened to the needle? See, I will show you before. The compass has a needle, right? Needle. One end is north, another is south, and is pivoted at the center. So it can rotate. Really, it can rotate this direction or this direction, clockwise or anti-clockwise direction. So we have a bar magnet here. In this bar magnet, around the bar magnet, there is magnetic field. Okay, so we are going to find the direction of magnetic field lines. So I kept a small compass here. So compass needle aligned like this. See, it is aligned like this. This alignment. This alignment, right? Why it is aligned like this? Why it is aligned like this? Alignment like this. See? Why it is aligned like this? The reason, the force is experiencing in this direction. So we have if you join all these points, we will get the magnetic field lines. But at this point, what is the direction of magnetic field lines? We can say that at this point, the direction is, this is the direction. This is the direction. Okay. Fine. Now, at this point, what is the direction? At this point, this is the direction. This is the direction. At this point, what is the direction? At this point, this is the direction. At this point, what is the direction? At this point, this is the direction. That is why we said that the magnetic field is a vector quantity. It has a magnitude and also it has a direction. So at this point, what is the direction of the magnetic field? The direction of magnetic field is the tangent drawn to the magnetic field lines at that point. So when a small compass is moved along a magnetic field line, the compass needle always set itself along the line tangential to it. So at this point, what will be the? At this point, see, the direction will be this. At this point, this will be the direction. At this point, this will be the direction. At this point, this will be the direction. At this point, this will be. See, it is not only in one direction. It is changing, right? Each point it is changed. How will you find? It is a tangential to the curve. At that point, you have to draw a tangent. Tangent means touching the circle, our curve. Only at one point, we have to draw a straight line. That line is tangent. So tangent will give you the direction of the magnetic field at that point. Okay, understood? Fine. So a line drawn from the south pole of the compass needle to its north pole indicates the direction of the magnetic field at that point. So suppose this is my compass. At this point, if you want to find the direction of magnetic field, what you can do? From this south to north, if you draw a line, this line is giving you the direction of the magnetic field. See, the same thing tangential. I have just shown you with this red line. Both are same. Okay. Suppose if you this want to find the direction at this point, this is the compass. We have just marked a point on the south pole, and we have marked the north pole, and after that we have just removed the compass we have removed. Okay, after removing compass, just join this south and north. So this will give you the direction of the magnetic field at this point. Clear, right? Okay. Now, to plot the magnetic field pattern due to a bar magnet by using ion filing. So this is a textbook activity given as 13.2. Let us go through that. Fix a sheet of white paper on a drawing board using some adhesive material. Here we have done a white sheet of paper. Okay, so we have just fixed it. Okay. Now, place a bar magnet in the center of it. So we have placed the bar magnet. See, down you can see the bar magnet kept below the cut. Sprinkle some iron filings uniformly around the bar magnet. Okay, we have used some sprinkler and sprinkling everywhere the iron filings. You know what is iron filings, right? A salt sprinkler may be used for this purpose, for easy purpose that we can do. Now tap the board gently. So below we have bar magnet, and top we kept a white sheet of paper which is sticked on a cardboard. Fine. And we have sprinkled using salt sprinkler. We have sprinkled iron filing. Okay. Now tap the board gently. Somewhere here or here we can just tap it. Okay, just tap. What do you observe? What do you observe? The magnet exerts its influence in the region around it. Correct? You have a bar magnet. Its influence will be there around it in the space. Correct? Therefore, the iron filings experience a force. Iron is a magnetic material. So magnetic interaction will take place on iron particles, right? Iron can attract. It can be attracted, right? So the force thus exerted makes iron filing to arrange in a pattern. So where the force of attraction or force of magnet is aligned, that region iron filings will be arranged according to that pattern.